I'm glad to have Georgia here to give us a presentation. So he's the director of the Nuclear Safety Consultancy from New Zealand for 26 years. And he works on the safety measurement, design to managing and control nuclear reactor accidents. And now he and his team are works with United States and European nuclear industries, the IAEA and nuclear safety authorities in the US, Canada, and Europe in working on nuclear safety and accident management. Today, he will give us a presentation about the IAEA Safety Standards and the beyond design basis accident and severe accident management. Now let's welcome Georgia.
Okay, thank you, John. It is a pleasure to be with you folks, either in the room or later watching the movie. As John said, I will give a lecture on a number of items in the nuclear safety and hope that you will be interested in following the matters. Well, I need to change the contents will be, I will first talk on the IAEA Safety Standards. Then I will give some impressions about lessons learned from the Fukushima accident, talk to you about some fundamentals of severe accident management, and to conclude a number of issues which I feel are relevant for future nuclear safety research. The IAEA Safety Standards. IAEA is the International Atomic Energy Agency, as you probably will know. It is in Vienna in Austria, so it's here in my hometown. And the agency is well known as the prime watchdog against nuclear proliferation. It inspects all nuclear sites in the member states, and notably suspect sites such as were available, maybe still are, in Iraq and Iran. You may recall those days in the early years of this century, the search for weapons of mass destruction in Iraq. And the agency said that no such weapons were found. The other side of the agency is the nuclear safety matter. So there's two, let us say, two major tributes to the agency, the proliferation and nuclear safety. And the agency has set up a set of rules and regulations for nuclear power plants, which are, I would say, a bit similar to the US Code of Federal Regulations on nuclear safety. And that is done for the member states. Well, US is also a member state, but they use their own regulations. Because the Code of Federal Regulation, of course, is well, intensively linked to US laws and regulations, which are not applicable in other countries. So therefore, this is a more, I would say, general approach. And therefore, other member states, for instance, Canada, China, Netherlands, and a number of other ones, use the agency regulations as their basics for nuclear safety. The Club of European Regulators, the VENRA as it is called, has concluded that they feel that the European countries should use the agency safety standards as the basis for their nuclear safety. This is the building of the IAEA in Vienna with all the member states flag, as you see. I'll talk a bit on the structure of the rules and regulations. They are, I would say, comparable to the US regulations, since that they have first general safety requirements, where they have 7 parts. Just mention a few of them. Part 1 is a government organization.
When we do the quiz on Thursday.
Part 1 is the government organization. That means notably for the countries embarking on nuclear safety, it is relevant for them, of course, to know what type of organizations you need to have a, let us say, a proper organization for building nuclear power plants. Part 4 is the safety assessment. How do you assess the safety of the proposal by the applicant? And part 7, also important, of course, is the response to emergencies. So those are the general safety requirements. Then there is a number of special safety requirements, and there I would focus on two very important ones. The SSR21 is the design of the nuclear power plants, and SSR22 is the operation of nuclear power plants. So the design of NPPs can be a little bit compared to the 10 CFR 50, the Appendix A, which has the US, the design features, design requirements for NPPs. And then we have a number in the agency rules and regulations, a number of safety guides, as the US has the regulatory guides. So here are the safety guides, there are 18 of them. A couple of guides are a response to an emergency. Number 2, the GSG 12 is staffing of regulatory bodies, so that the countries embarking on nuclear energy know how to set up a regulatory body. And the GSG 7, 8, and 8 are about the radiation protection. And then we have the special safety guides that goes more in the details, and there are hundreds. I just counted them anew. And number 7, for instance, talks on internal fires. And number as that is an old numbering, G222 is operational limits and conditions, which compares to the US approach of specifications. And the SSG 54 is the accident management for nuclear power plants and includes the severe accident management. Before that was the NSC 215, which maybe is used more widely. So a few things on the SSR21, the design requirements. The SSR21 addresses the design basis accidents, and I would say that is quite close to what you see in the US Code of Federal Regulations on the design of NPPs. So you see, for instance, requirement 19, design basis accidents are defined, and that is a set of accidents that you must consider in design. It shall be derived from postulated initiating events. And then you make sure that you stay below acceptable limits for radiation protection. So there are defined limits. The agency doesn't give you those limits, I must say. Each country must itself define the limits for their own application. But you must stay below certain limits for the design basis accidents. Then that is different for the design extension conditions. The agency there has added on the design basis event. They have defined beyond design basis events, which they call, excuse me, a bit different design extension conditions. And there, that is in requirement 20, then they say that you should consider, let us say, a number of conditions beyond the design basis with the purpose to improve further the safety of nuclear power plants. And in doing so, try to enhance the plant's capability to withstand without unacceptable radiological consequences, accidents that are more severe than design basis accidents. And you must, let us say, use these considerations to plan practical provisions for the prevention of such accidents and mitigation of their consequences. So there is no word that you must stay below certain radiation protection limits. You see here, you must make practical provisions for the prevention of such accidents. In practice, the agency requires the new nuclear power plants to make so, let us say, strong use of this requirement 20 that they have, let us say, outside radiation practically eliminated. That is the goal. So we practically will not see any consequence, any dangerous consequence outside the nuclear power plants. So these design extension conditions must be considered in the design. It is not a, let us say, a voluntary effort. You must do so. In the US, you have this 10 CFR 52 that also, let us say, gives you how to license a new power plant. And there is a few lines also that you should describe the matters which are there to prevent and mitigate severe accidents. But I found only 2, let us say, these 2 lines, not anything more. And nothing is said about that you should try to stay, and let us say, below or not have unacceptable radiation limits outside. The applicable regulation here is more soft than for the design basis events. For instance, for the design basis events, we have a safety classification, which is very strict. Because if you define a certain system to be safety class 1, 2, or 3, or as it is today in the US, safety related, then that gives additional high-level requirements for the manufacturing of the components of that system. For the design extension condition, if you have, let us say, equipment used to prevent or mitigate those events, then they lower, let us say, that safety classification, and they are satisfied with industrial quality. You can say for the more probable accidents, they require a very high level of defense. And for the very low probability events, it is satisfactory if you have an industrial quality. It must still work, of course, but you don't need to spend a lot of money on high safety classes of the dedicated equipment. Also, there is no single failure required. So as this is the DBA, for instance, you need 2 high pressure safety injection pumps and 2 low pressures and all this. If you have some safety equipment for the design extension condition, there is no redundancy required for the same reason as the safety classification is lower. And you do the analysis by best estimate codes. You are not looking for any conservative analysis, as you see in the 10 CFR 5046 and Appendix K on the ECCS. So you may do best estimate analysis. Although if I understood well, also in the US, they use now for design basis events more the best estimate type of analysis. The phenomena during a core melt, if you are not very well known, I will just list them for you briefly. First, we have an extreme hydrogen generation by the water-zirconium reaction. And I hope that you in Wisconsin University have success with your research on accident-tolerant fuel, because that would more or less make this hydrogen generation more mild. The core will melt by its decay heat, and that results in an immense release of fission products to the containment. That core may ultimately melt through the RPV lower head. And if that occurs at high pressure, then you are pushing around in the containment a lot of debris, extremely hot debris, and that may give you pressure spikes, which are known as direct containment heating. So that may threaten the containment integrity. If after the melt through of the RPV, the core is falling down, the corium is falling down in a water pool, then you may have a steam explosion in the cavity or in the pedestal for the BWR. And that may breach the cavity, may breach the containment. The molten core will also interact with the concrete, and it will, let us say, ablate that concrete, and it will generate large masses of carbon monoxide and carbon dioxide, which results, of course, also in pressure spikes in the containment. This is known as the MCCI, the molten core concrete interaction. So the containment overpressure is by a number of facts, either by the direct containment heating, by the hydrogen burn or explosion, or by the molten core concrete interaction. So you see, these are the phenomena which you somewhere must mitigate in your severe accident management. Here I give you a short view of those matters. Here you have the vessel with the core which is melting, and here it falls down in a eventual water pool, generating possibly a steam explosion. The hydrogen combustion is putting a lot of pressure in the containment. We have the direct containment heating, about which I spoke here, when the vessel contents is pushed in the containment atmosphere. So there is a lot of bad things that is going to happen. So here you see a few details of those processes. Here you see the steam explosion in the cavity of a French PWR. This is from a French monograph. The red sign is clear to me. I must say I didn't notice what the yellow would be. I guess it is somewhere a thing related to the steam explosion here. So this steam explosion can then destroy here the cavity, and it can even destroy more of the structure, and eventually the vessel may come down, or you may even over pressurize the containment itself. The molten core concrete interaction, you see here, there is an experiment where they have a simulant core which they melt then in crucible and let it interact with the concrete. Where you see here the result, this is the original concrete, and here you have the result of the of the core concrete interaction. In the right graph, you see the various also side wall ablation. It is not only that the corium gets down here, but it also moves out here. That is here not very well visible. It depends also, of course, on the experiment and the material you use. But in most experiments, you see quite a side ablation, and there are even investigators that believe that the side ablation is more strong than the vertical ablation, which in itself is not that bad, because on the other side you may have the water that was lost in the accident, and if you melt through the side, and that water may have a chance to cool this corium inside. Excuse me. Here there is a picture from the corium in the Fukushima reactor. I forgot which one it was, but you see it is some rubble and the larger parts. They also saw in one of the reactors there were quite large parts, basically, from the vessel internals in down there in the corium pool, which means that the vessel hole in the lower head was pretty large. So apparently there was a big ablation of the vessel while the core was leaving the vessel. The consequences of the design extension conditions, I will focus on what we did in Europe. Well, the design extension conditions remain clearly beyond DBA. That is, nobody tried to have the design extension condition inside the design basis. Some countries have established, by the way, radiation release limits. For instance, Sweden is so, and Finland. So they say you may also in a section not release more than so and so much radiation. Personally, I would say it may not be feasible to have such strict rules, because severe accidents and calculation is very a tricky business, and there is a large uncertainty associated there. So if you do the calculation, there will be a big margin, and it is difficult to demonstrate that you stay below certain limits. But what we do that different from the US, many countries here have required hardware features and hardware changes. And I'll give you some pics in the next slides. First, there were filtered vented containments. That means if the containment is overpressurized, then it is not just relieved to the atmosphere, it is relieved over a filter. There are hydrogen recombiners installed. The PARS, that is the passive autocatalytic recombiner. I'll give you a picture, which without igniting recombine hydrogen with oxygen. And of course, we have ordinary igniters, spark plugs, so to say. Then there are people that have a wet cavity, that is, they put a system inside so that they can provide water to the cavity to make sure that if the corium will drop from the lower head, it will see water and not concrete. And they hope in that approach that they will be able to prevent the molten core concrete interaction. Others are afraid of steam explosions then there. And I even recall that the French measure is not to do such a thing, as they are afraid of the steam explosion in the cavity. You just wait until the core is down there in the cavity and try to cool it by flooding it from the top, which may not be successful, by the way. And then, of course, we have the Severe Accident Management Guidelines, which is now also available in Europe. And in the US, it was not prescribed because the US industry voluntarily took on it to develop that themselves. About this method to prevent the molten core concrete interaction, there's just you put water around this vessel here, the lower head notably, of course, and by doing so you hope that the core will not come out and that you will be able to keep it inside, which of course saves you all the trouble of the X-vessel phenomena. There are various approaches to do this here. I won't discuss that here. This is a picture of the containment venting system. Here you see a big vessel of about 10 meters high, I guess, filled with water to halfway. And here is an inlet pipe that runs to a set of sparges here, down there with vertical tubes. And if you have the highly reactive atmosphere from the containment putting down here in the water, it will bubble here through the water. And there is even also a metal fiber filter, and release here the steam and non-condensable gases, and most of the radioactive material will stay inside the filter. Here is the passive autocatalytic recombiner, a thing of about 1 by 1 meter. You see here palladium plates, or plates I would say coated with palladium, and then that is a catalytic material which then helps to reduce the hydrogen or oxygen, to recombine it with oxygen without burning it. Of course, the outlet of such a machine is hot, so that means you must be very careful where to hang these systems, as you may easily damage, let us say, components which are nearby. So these are the devices which you will see in many European reactors today. The accident management, how looks that? Well, you will recall that there are probably 3 ranges of procedures. First, we have, for, let us say, normal incidents, the abnormal operating procedures, the AOPs. Then if we have safety injection or an emergency shutdown, we have after that emergency operating procedures. If we don't, let us say, can save the core in using these 2 sets of procedures, we understand we have a damaged core, and that brings us to the severe accident management guidelines. And please note the difference. For the first 2 conditions, we have procedures, which means you must follow them verbatim. And for the core damage accidents, we have guidance. There is no need to follow them verbatim. The US completed this severe accident management guidance already in 1998. In the rest of the world, that started later. And unfortunately, not all plants may have that yet. In 2011, Fukushima, for instance, had not complete set of operational SAMG available, which otherwise might have helped them quite a bit. Here is a diagram to understand it a little bit better, which I borrow from Westinghouse. You see here in the red an arrow, you see here the accident severity increasing from normal operation, transient reactor trip, and so on until core damage. And here you see the various procedures which you apply. And abnormal operating procedures and emergency operating procedures are there until core damage. They belong to the domain of the main control room, but once you are in the area of severe accidents, then most plants then shift the responsibility to a group of experts in severe accidents, which is the Technical Support Center, because the handling of severe accident management guidance is totally different from handling the operating procedures. And somewhere, of course, you start also the site emergency plan. Well, what about the lessons from Fukushima? Here I borrow from a lecture by Yasunori Yamanaki from CREEPY, which is something like EPRI in Japan. And for the accident management, he says the very first thing which you must have is you must have a comprehensive data collection. Evaluation of data is essential. I'll give you examples of how missed that can go, how totally wrong that can go. then there must be a smooth linking between the permanent equipment and the mobile equipment. Somewhere your permanent equipment will fail, otherwise you wouldn't be here in that accident. You must hook on then the mobile equipment, but you should know that you don't have much time to do that. Once the permanent equipment is stopping, you have not much time to switch on the mobile equipment. And here you see, for instance, that also in Fukushima, but unfortunately maybe in other plants as well, that to hook on mobile equipment within certain time must be exercised and trained, because a lot of things can go wrong. I myself saw once an exercise in the Netherlands where they tried to hooking on a portable equipment, and I insisted that they should do the test, and the people said, George, that is not needed. We know that there's a big hose and the hose will be connected to there. But I insisted that they should do the test, and when they were unrolling the, let us say, the big hose, then they found out the hose was 1 meter short. It didn't reach, let us say, the proper interface equipment. Now, what is also needed that all your mobile equipment is low pressure type. That means that you must be sure that you have a timely and permanent depressurization. And permanent depressurization is important because some of the processes may give you repressurization. Notably, if you put water on the degraded core, you will see a very sharp pressure spike due to the water-zircon reaction, which then takes place. So you must make sure that also in the repressurization phase that you can get rid of the high pressure. And there are still some plants in the world that don't have, let us say, depressurization valves. So the relief valves, which you can, let us say, operate from the control room, and then they are in bad condition, as you will see. What was most, let us say, typical or astonishing, I would say, is that the delayed water injection may cause the core to melt, where you would assume that water injection would stop the core degradation. No, it even enhanced core melting, as we'll explain later. And then it is needed that you know how your equipment functions. For instance, in one of the units, I believe it was unit 1 in Fukushima, they used an isolation condenser to cool the primary system. But nobody ever had seen that system operating. So when it started to operate, it pushed an enormous amount of steam outside of from the vessel, which is there connected in the isolation condenser. And the staff was so afraid, excuse me, that there was a leak from the primary system that they isolated the isolation condenser. So that means that they basically removed the decay heat removal system, which caused then later the core to melt. So here I'll let you show, if you take me, I take some emergency cooling myself. Here you see the difference between actual and observed data. Here you see what the observed level, the water level in the reactor pressure vessel of the unit 1, where this is the top of active fuel, and here below is the bottom of active fuel. And this is what I saw in the control room. But when they finally analyzed the whole thing on the basis of the data, the analysis gives somewhere here, or in these two curves. So it means that the measured data were totally and fully off reality. That is one of the important things in severe accident management guidance. You must have instruments that somewhere tell you the truth, or if they don't tell the truth, that you know what the deviation is. I saw some of the SAMG is indeed telling the people that this or that instrument in the severe accident will give so and so much, many percent, let us say, difference in the reading, but a number of them only say you may see a different reading, don't trust the reading. But that, of course, doesn't help the operator so much. Here is the most typical process in the unit 2, where they were injecting with the mobile pump, and by injecting the water, they run above the pressure of the injection system. So the injection was stopped, And then when the pressure went down again, the pressure came up again, the injection came up again. And here in the, it was a large amount of steam generated and hydrogen generated. And that caused an immense heat in the degraded core. And it is believed that that's enhanced the core melting. So the fuel melted as a consequence of the injection of water. That is the thing I believe operators must know, that the moment they understand the core is gone, that they should give them guidance what to do. Either put so much water that you immediately quench, or don't put water in the core, wait until it melts through the bottom and then take your measures there. So those are the things that must be evaluated by the technical support center and then lead to a conclusion. So some fundamentals of the severe accident management, I would say, before I said it is so different from EOPs. Well, the EOPs tell you how to protect the reactor. So they have you all types of means to make sure that the reactor will not be overheated, that you will keep it cool, and that you keep it shut down. That now the core is lost. It doesn't mean that you must stop your exercise there, but your attention should shift from the core to the fission product barriers. So your first and your prime attention must be the integrity of the remaining intact fission product barriers, because I would say the SAMG is not to protect the core, but to protect people. Just that, something totally different. Another thing which is very typical for the severe accident management guidance is that some of the actions may have very severe negative consequences. Usually the actions in EOPs are beneficial. If you do them, they have success. But here, they may have very bad consequences. So an example is a containment spray, which is a very useful thing in EOP domain. But if you have also hydrogen there, and you have a lot of steam, the spray will take away the steam and then may invoke a hydrogen burn. And you may lose your containment right on the spot. That's the reason why we have guidelines, because we must then consider to stop a thing which we usually in EOP domain do. In EOP domain, we would just put on the containment spray. In SAMG domain, you would put it on up to a certain level where you know, now if I spray more, I may have a hydrogen burn. The consequences because of this, let us say, complex matter is that we shift the responsibility, as I said, to the severe accident specialists, which are usually in the so-called technical support center. I already said to you that you must have caution on instruments because they may give fake data. I'll give you an example there, and so it is extremely important that you, when you read instruments, that you know how to read them, how they deviate under the given conditions. And even worse, I would say the most SAMG assumes that your AC is lost, but your DC is there. Your DC is still there. And that I criticize that assumption, because if you really have a big trouble in your plant, you may also have lost your DC. You may have lost your batteries, and then your instruments are dead. Now, if instruments are dead, then of course you must go back to your knowledge base and more or less try to understand what is going on. If you have some impression about how severe accidents evolves, what evolution of a severe accident is, you can say, my core will melt in 1.5 hours. And in 6 hours, I will have a melt through of the reactor pressure vessel. And in 8 hours, my containment will fill. Those things, you have that from your PSA. So you must have some understanding of the severe accident, because your instruments may fail to give proper indications. What is also important is that once you are there in the severe accident, you must assume that there will be some releases somewhere during the accident, and you should try to predict the magnitude of those releases and inform authorities so that they can take their appropriate measures. If you fail to do so, the authorities don't have another option than just evacuate everybody around to a large area, which in itself causes an immense trouble. And I mean, please do not consider that you must evacuate a hospital in the middle of the night suddenly, yeah, that you take all the people away. I mean, that will give fatalities, that will give accidents. And so it is extremely important that you are able to tell the authorities to what level you will see a release. And I must say, my friends, that unfortunately, quite few plants are capable to do that. I mean, there's to predict outside consequences. That means to say in 2 hours or 3 hours, that or that will be the release, is an extremely difficult condition. I'm aware of some work in France that is trying to, let us say, to make a sort of computer code where they read from instruments which are still there, and let us say from those plant data, they read more or less the condition of the reactor, and from there they try to predict then the outside consequences. Of course, this is a difficult matter. The thought process of SAMG is totally different, as you will have understood, from the EOP, and I give you an example of the different thought process. You will recall the Titanic hit an iceberg in 1912 and went down, although it was believed that the ship was unsinkable because it had these watertight compartments, 15 or so of them. And the ship was designed in such a way that it would stay afloat with 4 of these compartments flooded. If you would flood 5 compartments, you would go down. Now, what happened when the captain discovered there was an iceberg ahead? Then he did his usual, let us say, maneuver, that is, move out. Yeah, so he went to left or right, I'm not sure what he did in reality. But he tried to avoid the iceberg, but because he was too near, he was unable to really avoid it. So he hit the ship on the side here and opened up 5 of the compartments. So then that means the ship was lost. They understood already long before the ship actually went down that she would founder. What should the captain have done? He should not have tried to avoid the iceberg, but should have hit head on. In that case, he might have damaged the first compartment, maybe also the second, but guess it would probably have been limited to those 2 compartments, and the ship would have stayed afloat. Now, you can imagine what is the difference of response. The usual response, of course, is move out. So this is what people do. This is what you do by instinct. But the SAMG tells you this. If I would say if this would be have written, it would have been SAMG. The SAMG would have told them no, hit the iceberg head on. And that is a way of thinking which is fully different from, let us say, everything in normal operation. So the thought process in SAMG is different. And this is, I must say, when I did various reviews of SAMG, which I didn't observe really in the plant, most people treated the SAMG as EOP. They didn't change their thought process. And you must do that. If you are unable to do that, if you are unable to move out, you will be a Titanic and will founder. I give now a few last words on what I consider relevant items for future safety research. I was invited to write an article on future safety research on the long term, so in the upcoming decades, by Professor Dauria of the Pisa University in Italy. And I did so, and that will be published in Nuclear Engineering and Design in a couple of months from now. And to give you a few items of that article, the article is about 30 pages long, so you have some reading there. One of the things which I observed is that we should better understand the scaling laws, because a number of insights in reactor behavior, in the physics of, let us say, the processes of core damage and core melt and all this is obtained from experiments, laboratory scale experiments. And then the computer codes have been designed that then take all these effects into account, and so more or less are capable to hopefully predict what will happen in a reactor case. But here, my friends, I would say one should be extremely careful, because what you have measured on small scale, what you have seen in small scale, may not be the same as what you would see in a real event. So you must also investigate the scaling laws. And unfortunately, this is a thing that I saw only very few times. People more or less extrapolate their findings from laboratory research into the reactor case, more or less one-to-one. And that, I believe, is something that absolutely should be resolved. Then a number of severe accident management features are present in present-day nuclear power plants, new nuclear power plants, such as the IVMR, which means the in-vessel melt retention. It means you try by flooding the outside of the vessel to keep the molten vessel inside, molten core inside, as I explained. They assume it works. A number of people, notably in the boiler case, have a lot of water underneath of the reactor pressure vessel, and just to cool the core if it comes out. But what happens if you have a steam explosion? They just assume there is no steam explosion. Now, I must admit, steam explosions are improbable events, that's for sure. But if they happen, they have extremely severe consequences. If you look to the forging industry, the iron and steel industry, there have been many steam explosions there with devastating consequences. So the steam explosion is not a theoretical event. But here we assume, for some reason, that we won't see it, as we assume the IVMR will work. And I guess that those severe accident management features should really be validated, should make sure that they work. Otherwise, we are, let us say, misleading ourselves. Then I would say, what is basically what people are afraid of? Radioactive release is terrible, of course, as it can cost human lives. But what we saw in Fukushima is the radiation was not so big that it would cause any fatalities, but there was an immense and total social and also economical disruption. There were many fatalities in the evacuation process around Fukushima, and the economical consequences were even more severe, I would almost say, if you may compare these two, because all the nuclear power plants had to shut down because of they had to reconsider the safety. So the consequences of a severe accident are not only large release, but they disrupt the functioning of society. And you should somewhere include the avoidance of societal disruption in your safety rules. Not just talk on large early release. No, there is more to consider. There is also a societal and economical consequence to consider. There is a big report written by the ASME under the leadership of Professor Niels Dais. He was the former chairman of the US NRC in 2012, and I can everybody recommend to read that report and make sure that we never will see a Fukushima, the next Fukushima. If we see a next Fukushima, my friends, I'm afraid that will close down much of the nuclear energy efforts, because the society is not prepared to take this type of accidents. No. What is associated there is that you should make the regulation more risk informed. And also a big report is written by Commissioner George Apostolakis on how to make the regulation more risk informed. And the reason to do that is that we now have a lot of things in our plants that are never used, because our safety features are there to meet and mitigate the large break loci and similar effects, whereas the actual events which we have seen are more, let us say, developed in a certain scenario which we didn't consider in our deterministic regulation. And it means we have no protection against these, let us say, higher risk scenarios. So we should make our regulation more focused on the real risk that the plant has. And that is the message of George Apostolakis in this document. And I would say it's also my message for future research: make you go away from the deterministic regulation, which we have now, and go the risk-informed way. I would say I'll see also in the US NSC regulation that there is a number now of reg guides, the reg guide 1200, I believe, and its follow-up that gives you information how to use the PSA, the PRA in the US language, to make sure that your safety features indeed match the risk of the plant. For Gen 4, a number of you, excuse me, for reactors, I would say we have there a lot of exotic materials. We have molten lead and molten sodium and salts, and so we have seen a lot of trouble in the LWR technology in the past 60 years with as simple system as water steam. And it took us 60 years to understand, let us say, those phenomena. So we must make very sure if we're running reactors on exotic materials that we have at least understanding of the degrading mechanism as far as possible, because the clients and the utilities that want to build these plants, they want to run them for 30, 40, 50, 60 years. So we are not yet that far. So our Gen 4 reactors haven't run that long time. So that means we must somewhere convince the clients they can make it. So this is one of, I'll have to say, one of the items which I believe also is relevant for your institute, that make sure the reactors are robust and will work for a long time. Okay, that brings me to my last slide, which is very short. If there are any questions or comments, I will be pleased to hear. Thank you for listening to me.
Thank you, Georgia. It's a very impressive presentation. So any questions from the audience?
You may also send me an email, of course, if you believe the question is more complex or otherwise.
Yeah, thanks. That sounds good. Yeah, I have a quick question for you, Georgia. In this work, you talks about a lot of efforts on the severe accident for the light water reactor under the structure of IAEA. I'm wondering if IAEA is making any efforts on the severe accident research for the advanced reactors and or maybe micro reactors, things like that, small modular reactor.
I'm not sure I understood your question. The IAEA has, let us say, a limited research program. They more or less rely on the expertise of the research done in national laboratories. They have some limited research, that is true, coordinated research program they have, but it is not, let us say, a creation of knowledge on this type of work. So they assemble, let us say, information that is around, and they produce reports there. If you see also the so-called tech docs by the IAEA, you see there the newest insights of the let us say, the latest designs. I would also refer to the not only to the IAEA but to the OECD, Nuclear Energy Agency, the OECD, and EA, Nuclear Energy Agency, where they produce state-of-the-art reports on the let us say, most recent designs. So if you go to their website, you will see the latest public reports. And if you are a member there, then you can also go to some of the still confidential reports. Not sure whether I answered your question, but I hope it gives you a certain direction.
Okay. Sounds good. Thank you. Okay.
Any more?
Yeah, go ahead.
Apparently I was quite clear. That doesn't happen so often.
We have more question. I got a question here. Can you hear me okay?
Yeah, sure.
So going back to your Titanic example and the process map of going from your procedures to the severe accident guidelines, I guess it seems like you're, and at what point you hand this over to the technical staff that is well versed in the severe accidents. It seems like it's the call of the operating staff to make the decision of either plowing through the iceberg or trying to get out of the way. But it seems like only the severe accident or the technical staff would really know whether or not that's the best route to go. I guess if you could just walk through the process map a bit more on how it gets handed over.
Sure. Let me explain. I didn't touch that, but there is a whole process behind the so-called transition from EOP to SAMG. I mean, that must be, first, it must be documented, it must be investigated and documented, and it must be trained. In a number of cases, it is the operating crew in the control room that says, we now lost control over the reactor. We give the reactor now in the hands of the technical support center. But it can also be that it is written that only the site emergency director may make such a decision. Of course, he will consult his people, but it is nobody in the control room is allowed to make that decision. It is the site emergency director who will make that decision. So this, let us say, the system of how to transfer from EOPs to SAMG is a quite complex system, and it is trained and documented and trained. And I can tell you, I observed a number of exercises where this was trained and it ran wrong. That means some people believed they were still in the EOP domain, others felt they were in SAMG domain, as they had missed the transition. So the transition is extremely important. You must have criteria to do that, and the criteria must be clear, and everybody must understand them. And also, if let us say, if you are in a real event, or let us first say, if we are in an exercise, when the transition is there, you must make sure everybody understands it is there, so that the decision to go over from EOP to SAMG is clear and univocal, I would say, so that there can be no misunderstanding where we are, because the response in SAMG domain to what you see in the reactor can be totally different from what you would do in EOP domain. I gave you the example of the containment spray, which can hurt you very severely in a severe accident. Is that answering your question more or less?
Yeah, thank you.
Okay, thank you.
I have a question.
Go ahead.
So I've noticed, I really appreciated the example of the Titanic, where in the case where the captain did what his instincts actually caused more damage than the counterintuitive solution to the approaching iceberg. And I've noticed that in the nuclear engineering industry as a whole is less, there's less of a focus on user interaction with the technology as compared to software or as compared to other fields of engineering. My question is it worthwhile for the nuclear engineering industry to adopt a significant, or to put significant research into user experience, user interaction, behavioral economics, as it were? Is it worthwhile for us to do that?
Yeah, I would say absolutely. I noticed myself, I gave once a lecture in Switzerland for a number of nuclear power plants about severe accidents and severe accident management. And I recall I was talking on melting cores and all this, and I saw the director of one of those plants getting, his face became more and more red and became purple ultimately. And then he shouted, "George, those accidents don't happen here." So you see, the first thing you must overcome is the misbelief. People believe the accident doesn't happen here, or it happens with the neighbor, somebody else. No, I'm not hit. So the first thing is people must be aware the accident can be there. And let me tell you that after, let us say, or a part of the severe accident research goes in human engineering, because I wouldn't call it the user approach, but human engineering, as it is difficult to make sure that the people will react properly. For the EOPs, you see, we always assume that if the operator takes an action, that action is successful. He understands the action and he does as he should do. But we saw in the various events that that is not the case. The people react in panic. They are afraid. They are confused. They have confusing information also. So that is the moment that you must somewhere, you get a human element inside. And that human engineering is nowadays is quite a big part of the, let us say, the safety research. It may not be very well known to people that work with codes and hardware and experiments, but there is also, let us say, on the psychology side and the sociology side and research going on how humans behave in severe circumstances and how you can more or less, let us say, influence that. Assuming that even with the best human has a probability of making errors. So I hope this gives a little an answer to your question.
Yes, thank you.
Okay, thank you.
We have another question from the chat channel, if you can read it.
Mm-hmm.
Did you find it?
Oh, sorry. Should you look in the chat?
Yeah.
Okay.
If you open the chat.
Okay.
channel.
Yeah, I have the chat. Huge myth to everyone. I especially appreciate your request to address societal disruption and make regulation. Yeah. Our experience is that lawmakers really, let me see whether I can appreciate meeting with researchers when we're reliable, informed about this technology. Are there organized efforts to pursue this at both congressional and legislative level? I'm afraid this is the question is restricted a little bit to the US situation. So I would say I don't know what happens in the US, but I understand at least there is contact between the various, I would say, players in the field. So it means the ones that make the rules talk to the researchers, and the ones that make the nuclear power plants also talk to the researchers. But I would say that personally, I've found that, for instance, the interface between research and severe accident management is weak. I recall one of the major developers of SAMG, of severe accident management guidelines, once told me, George, severe accident management guidance, that's no research, that is engineering. So you see, that is of course not true. I mean, it is based on research, and without research, you're putting the wrong things on the paper. So there still are gaps between the various branches in the nuclear science, in nuclear engineering. You see on the one side, you see the vendors, then you see the researchers. The researchers, they usually living in laboratories, and the laboratories want more research because that's what they live on. But whether that research is needed for the nuclear power plants or not is maybe not the first question they have. On the other side, the vendors have a limited talk to the researchers, unfortunately. They believe that research, yeah, our plants are there, they're safe, so what are you further researching? I noticed in my experience that it's a mutual respect of the various groups is limited. Everybody lives in his own world and doesn't talk to outside. In my article on the future safety research, I also talk on this fact that there is a limited contact between the various, I would say, groups that together should form the basis of nuclear safety. So it should be improved. What is there is maybe already a basis, but it certainly should be improved.
Okay, thank you.
Okay.
So if there's no more questions, I think let's thanks again for Georgia. And thanks a lot for your presentation at the University of Wisconsin-Madison. I'm very appreciate your time here. Hope everyone have a great afternoon. Thank you.
Okay, thank you, John. It was a pleasure. And sorry, I interrupted lunch for people, but you interrupted my beer. So, okay, we are on the same footing. Nice to talk to you, friends, and hope to see you soon again. All best to you. Thank you.
Talk to you later.